Hello everyone, my name is Rishu Sharma and I'll be talking about analysis of error correction control coding schemes for wireless communication systems. The course code is EEL6509 and my course instructor is Dr. Dapeng Wu. This presentation is a part of my final project for the course. I'll start with introducing wireless communication systems. In modern day wireless communication systems, robust system design plays a crucial part in determining the quality of data transmission on the channel. Especially for wireless networks, the noise introduced in the channel is very high due to interference, fading, shadowing, etc. At the receiver, the demodulator must employ error correction techniques to curtail majority of the errors to reconstruct the signal before sending it to the amplifier or analog converter. It is interesting to note that wired networks are not susceptible to the same losses and are more reliable. In order to ensure efficient transmission at an optimal speed and acceptable time delay without burdening the system infrastructure, all the aspects of system design like source coding, error detection, frequency modulation, filtering, equalization, and channel modeling must be well designed. In this presentation, I am going to target the aspect of error control coding in digital communication systems and analyze various error detection correction schemes like CRC, BCH, LDPC, Reed-Solomon, and turbo coding. I've also included two applications in the project. So why are we doing why are we doing error correction in the first place? To reduce BER or bit error rate. Bit error rate is the rate of erroneous bits received in a given time frame. Low bit error rate could be achieved by high SNR, superior modulation scheme, or error correction coding. But it is not advisable to design a system with high SNR for low BER or choose a modulation scheme based on BER. Let's see why. We'll talk about signal strength first. So, we can see that in order to maintain a low BER, the EB by N0 should be really high. So the Shannon-Hartley capacity theorem for wireless system states that data can be transmitted at a rate R which is less than C. So R is the rate and C is the capacity. Channel capacity in bits per second. The probability of error could be kept small with a sufficiently complicated coding scheme while maintaining a bandwidth of B Hertz, this is B. As obvious, we reject this premise because high signal strength requirement burdens the system, and also another thing is that transmission power must be very high for long distances. So that leaves us with superior modulation scheme as second option. Now, modulation is decided based on rate, bandwidth, carrier frequency, distance, filter performance, and type of modulators. Let's run a simple program to plot BER versus SNR plot for BPSK modulation to reinforce what I just said. So here it is, and this is just to plot BER versus SNR. I'm just going to plot it. So this is what we get. So this is the simulated data and this is what we expected theoretically. Whatever, it still says that in order to have a low bit error rate, the SNR should be really high. Okay, let's get back to the presentation. Fine. Now, in order to achieve same BER for low SNRs, superior techniques like QPSK, QM, etc. would be used. So even modulation looks like a cause not worth fighting for BER. Now, at this stage, error correction control comes to rescue. This is a block diagram that you see here for a transceiver system in a communication channel. Source encoder is responsible for eliminating the redundancy in the data. This is the source encoder. And channel encoder introduces controlled redundancy to curb the errors that result from channel noise. So a combination of error detection and correction is employed in a transceiver system to rectify the corruption in data received. Okay, let's get to error detection schemes. Error detection schemes are employed to detect or identify errors in a channel. A few of the widely used schemes are here. Repetition codes, parity bits, checksum, cyclic redundancy check, CRCs. and I'm going to detail CRC with an example later on. Right now, I'll just brief about these techniques. So repetition codes, they divide the data into blocks of bits and repeats the transmission of these blocks over and over again to ensure error-free communication. Thus, if the same block is arrived at the receiver thrice, and the fourth block that the receiver has received is unlike its predecessor blocks, then I can easily say that an error has occurred. Parity bits. A parity bit is just added to a group of source bits so that the outcome is even or odd. Third, checksum. A checksum checks the length of message code words. These schemes consist of check digits, parity bits, and longitudinal redundancy checks. Now your CRCs or cyclic redundancy checks. They perform single burst error detection to detect unintentional changes in digital data. A CRC divides the input data by a generator polynomial and yields the remainder as a result for error check. They're popular for rectifying corrupt data in digital networks and storage hard disk. So now let's run a small program to plot the length of information bits versus CRC generator polynomial order that I just talked about. What you see here, we're going to plot it. Okay. So yeah, this is the code for just plotting according to generator polynomials, and we're just plotting it, and here is our figure. So what does this plot tell us? This plot tells us that the performance requirement for error correction increases. If that happens, the number of bits to be transmitted dips linearly on a logarithmic scale. If there is a restriction on storage capacity and there's not enough memory in the device to support error tables, then there's a problem. The capacity of the scheme will further decrease. Okay, let's get back to the presentation. Now, after we've done error detection, we come to error correction. So after the error has been detected, what could we possibly do to do the damage repair? So we have two schemes here. ARQ is automatic repeat request, and correction codes is another scheme. ARQs. So error correction is performed either as a preventive measure to avoid error from being incorporated, that is what ARQ does, or once an error is occurred, it has to be corrected through a separate mechanism, that is forward correction coding or error correction coding, that we'll be talking about. So I'll just give a brief description of ARQs and quickly go to the correction codes. ARQs or automatic repeat request, they utilize error detection codes, acknowledgements, timeouts for transmitting data in a reliable fashion. ARQ is a technique which is employed for avoidance of data corruption. So they are well suited for channels with unknown capacity, but then it has its own shortcoming. And the major shortcoming is that this technique tends to add additional strain on the network capacity because of its high maintenance and multiple retransmission requirements. Okay, correction codes. Error correcting code, which is also known as forward correction code or FCC. They add non-essential data to a message when multiple errors are introduced in the transmission. So these are mostly used at the lower level of the communication stack. Since we are exploiting the channel capacity by adding the surplus data, Shannon-Hartley theorem that I talked about in the introduction becomes crucial in determining error probability and SNR. The code rate is equal to K by N, where K stands for source symbols and N stands for encoded symbols. FCCs are broadly divided into convolutional codes and block codes. Convolutional codes, they are processed on every bit individually. They are used in memory-based systems. And the examples of convolutional codes are Viterbi and Trellis. I'm going to run a simple example of convolutional code to depict 3-bit soft decision decoding. Okay, so this is the program, and a convolutional code is created here and white Gaussian noise is added to it. Then quantize this. It's used to map the noisy data values with a suitable decision. So this value can be random between 0 and 7. The partition vector is decided such that the values surrounding 0 map to 0 and those around 10 map to 7. Decoding is carried out and BER is computed. the decoded data is compared with the original data. Now, since there is a decoding delay of traceback distance, the decoded message's length is traceback length plus 1 rather than the expected length of 1. So we expected to get a number between 0 and 7 and we got 5, and the error ratio comes to be 0.0013. So looks like works fine. Okay. So this was about convolutional codes. And now I'm going to get into the details of block codes. Now, other category is block codes. They process data block by block. A block is a chunk of predefined number of bits, and this is a system of memoryless codes. Now, I personally like block codes because of their simplicity and optimal efficiency. So there are different types in block codes also, like Hamming codes, Reed-Solomon codes, BCH, turbo, low density parity check codes, etc. And so let's talk about BCH. BCH belong to category of cyclic error coding correcting codes constructed using finite fields. During BCH code design, the number of error symbols to be corrected can be controlled. BCH codes use syndrome method for decoding. So I have a file .bch.m, it's a script file, and it will illustrate encoding and decoding data using a BCH code. So the output checks and detects one error. This is how it goes. So this is BCH. It's going to check and detect one error in the output. Yeah. Now, I'll run another file. So this file is bchcorrect.m. So this is going to correct the number of errors in the BCH decoder. So what happens here is that some data is encoded followed by introduction of errors in each of the code words. So I'm introducing errors with the help of noise here. And the noisy code is decoded using BCH decoder. The array of noise contained binary values. An addition operations noise takes place in Galois field. Non-zero value of the final non-zero value points out that decoder corrected the corrupted code words and recovered original. So if we run it, this is what we get. Yeah. So the values in the vector is the corrected number of errors in each code word. So in each code word, one error was detected. So here I had taken 6 number of words, so I should get 6 corrections. So this is exactly what I get, 6 corrections. So works fine. Getting back to our presentation. Let's move on to Reed-Solomon codes. Now Reed-Solomon codes belong to the class of cyclic error correcting codes. They are capable of correcting multiple symbol errors. If we add n number of symbols, Reed-Solomon can detect up to n by 2 errors. So I'm going to run a script file rs.m that shows encoding and decoding data. It's similar to what we did with BCH codes. Here. So this again is going to give you the number of bits it corrects, and it corrects 2, but it does it cyclically. So this is what we get here. Now this is another file where we are going to not just detect the number of errors but actually correct them. So again I'm doing the same thing. I am passing it through an encoder, then adding the noise and then decoding it. So what should I get as results? So when I run it, yeah. So again, the non-zero value of the output confirms that the decoder was successfully able to carry out the correction operation on the noisy data. And these values, they indicate the number of errors corrected for every code word. And we took 4 here, so you should get 4 corrections, and this is exactly what we get. So works fine. LDPC codes. LDPCs are low density parity check codes, and they are linear error control codes. They have sparse parity check matrices and long block lengths to attain performance, bordering Shannon limit. The process of decoding is iterative, so a decently high number of iterations are required to make the algorithm converge. So now we are going to see the script code for LDPC coding with PSK modulation in additional Gaussian noise channel. I mean, I have added the additional white Gaussian noise to the channel. So the problem in running this code is that the output takes painfully long time because it has a very high number of iterations, but I'm going to run it nonetheless. LDPC, so I run it. And you can see what is happening. Just need to be a little patient. Yeah, so you can still see here that the system is still held by the program and it's going to be held for a pretty long time. So I have already done the simulation and these are the results I get for LDPC. So I get 1250 frames. So these are the number of errors that I have detected and I have been able to correct these many errors. Alright, now, so this is the block diagram for LDPC codec, LDPC encoder, modulator, channel, demodulator and LDPC decoder, the usual flow. Let's talk about turbo codes. Turbo codes, so here is a flow diagram for turbo codec. Turbo codes are considered very powerful for error control since the performance has close proximity to Shannon's limit. Now these codes could be concatenated or iterative. And I'm again going to run a turbo code and that is going to take very long time because of large number of iterations, just like LDPC. So I run the turbo code. And it's going to keep on running and keep on iterating, and you can see these values are going to keep changing with time, and I'm just going to move on because it will take a lot of time and I'll tell you the results that I got with simulation. So the error rate is 0.129 and the number of errors are this. So since we had total number of bits as 10,000, it totally makes sense to have this error rate. And later on the noise variance converges to 6. It's going to converge to 6. Oh, it already has. Fine. This didn't take those many iterations to converge. But I'm sure the LDPC code is still running. See, it still is running. Okay. So this was all the theoretical part. And now I come to the most interesting part of this entire presentation, that is the application. So what are the applications of error control coding? So especially in wireless networks and wireless communication systems, they find wide variety of use. Let's take TCP/IP stack for instance. CRC checksums are widely used across the TCP/IP stack for checksum corrections and calculations. Then for satellite and bandwidth communication systems, we know that bandwidth requirements are pretty stringent and percentage error introduced in the channel is also very high because of the enormous distance of propagation. So ECC schemes like Galois, Reed-Solomon, Turbo, LDPC, they find good use there also. So now let's talk about applications which we can illustrate and see through code. So what I'm trying to do in application 1 is I want to transmit and decode data for an 8 DPSK, differential phase shift keying, modulated channel, and I want to use BCH encoded signal to count the number of errors. So the reason I have chosen this example is because I personally like BCH, as I mentioned before, because of their uncomplicated design and low power hardware. So this code is already available in MATLAB examples. So if you want, you can have a look there, but I'm just going to run it and show here. So this is my DPSK modulator and I've added white Gaussian noise to it. Now I'm going to see how BCH encoder works and I'll see the error rate and number of errors. Okay, so the error rate is 0.00832 and the number of errors is 25. So the thing is, number of errors is generated randomly and depending on that the error rate changes. Alright, okay, now the second application. So the second application that I am doing here is, so I had this idea of transmitting an image over a noisy channel and I wanted to use Reed-Solomon encoder decoder to curtail the errors at the receiver and reconstruct a resized but clear image when compared to the transmitter. So I'm going to quickly run you through the code and then show you the outcome of it. So this is the code. Yeah, this is the code here. So what I'm doing is I'm resizing the image. I've like n and k. N is basically 2 to the power m minus 1, where m is a number of bits, so it comes around 255 since I'm taking 8 bits, and I'm taking k as the code word length, message length, and that is 245. So code word length is 255, message length is 245. So n and k are the parameters that the decoder and the encoder would be working on. So I'm reading an image and I'm resizing it so that I can pass it through my decoder, and it's then encoded. So here I'm just converting it into a column matrix for encoding, because RS scheme needs a column matrix. Then this is just for encoding, and here again I'm transposing and reshaping to get the original, because I had converted it to column matrix before from a square matrix. Now I again need to convert it to a square matrix or something cross something matrix, depending on whatever my dimensions are. So this is what I do here, and when I run it, so then this is the encoded C2. This is the encoded image, and now I'm going to introduce noise. So you can see that I'm randomly introducing noise in the channel, and this has, over the noisy channel, the image has got noise, so it's going to get blurred or it's going to lose its resolution. So this arrives at the receiver here, and when this arrives at the receiver, it's pretty blurred. So after we pass it to the decoder, it should be easily able to reconstruct it to a good extent, or get rid of the errors. So I'm going to run the simulation so that you can see what I was talking about. Okay, so this is my original image. So this is my C2 here, the first figure that I run. Oh, sorry. Yeah, the first figure that I run here. This is the original image. The second figure is after the noise has been introduced. So you can see that there's a lot of error points here. So this is my figure 2, immediately after the noise. Then comes my figure 3. So you can see here that this has become better. So this was the original image, this was after error, figure 2, and this is after it has been passed from the encoder. So here, so I'll show it again: original image, erroneous image, and after RS encoding, it reconstructs. Alright. So after the corrupted image is passed, the codec corrects n by 2 errors, and the image is finally, which we obtain after error correction coding, is commendably better, as you could see there. So I would like to conclude here by saying that whatever we saw as concepts, I mean, we could apply error control coding, and based on that, we can say that error control coding is an indispensable technique to improve the overall quality of the received signal without taxing the system design requirements. I'd also like to add here that it would be really inconclusive to try to determine superiority of one coding scheme over another coding scheme, because based on various scenarios and factors like length of the frame, error in the channel, modulation type, number of iterations, and amount of redundancy addition, a suitable error correction scheme must be chosen for an optimal performance. So finally, I take leave by thanking my course instructor, Dr. Wu, for his support and guidance. Thank you for watching this video. I hope you found it informative.